Lesson 1.5 takes what we know about solving systems of equations and transfer that to systems of linear inequalities. A linear inequality system will have a solution that is a region on the graph versus just an ordered pair. To get that solution on a graph, there we go. To get that solution, we'll graph each inequality separately. You'll always want to get y by itself, and you'll want that on the left-hand side. And in our first example, y is already by itself, so we're in great shape there. The second thing you want to do is just graph each inequality separately, and we'll shade as well. You have a solution to the system if the shading overlaps. If the shading doesn't overlap, then there's no solution. So make sure that if there is a solution, that it's visibly the darkest region in that set. So the solution should be very clear. Some students like to just shade where the solution is and not shade anything else, and that's absolutely fine. Just make sure that you're showing some sort of understanding as to how you got your result. All right, let's try a couple of examples and put this to the test. The first graph, y is greater than 4x minus 3. I'll start with that one. Notice that y is already by itself on the left, so I'm going to sketch that inequality as a line, y equals 4x minus 3. I notice there's a y-intercept of negative 3, so I'm going to plot that, and the slope is positive 4. That's a really steep slope, which means I'll count up 4, 1 to the right, and keep repeating that process, and I'm going to go all the way to the edge of my graph. I'm going to do the same thing in the opposite direction, over down 4, 1 to the left, and then that puts me a little bit off the graph. Now looking at the type of inequality, because of that inequality, my line is going to be a dashed or dotted line as my boundary. Kind of like an open circle if it was plotting a point, but since it's the entire boundary line, I'm just going to draw a dashed line through those points, or a dotted line, whatever you want to call it. Arrows at the top and bottom. And now we need to shade. So now we have to think about, what does greater than mean? Look at where it crosses the y-axis at negative 3. Values for y that are greater than go up on the y-axis. Values that are less than would go below. So what this means is we'll shade above the line. I'm just going to lightly shade in everything on this side in orange. There's that portion of the graph. And now I'm going to take a look at the second inequality. Y is greater than or equal to negative 2x plus 3. And again, y is already by itself, which is good. I'll plot positive 3 up here on the y-axis. And my slope is negative 2, which means I'm going to count down 2, 1 to the right, down 2, 1 to the right, and again, repeat that all the way to the edge of my graph. I'll do the same thing in the opposite direction. Those points represent the boundary for my inequality. Because of greater than or equal to, now my line will be solid. I'm just going to connect my dots all the way through my graph, like so. And now what it means to be greater than, y is greater than or equal to my line. Again, go to the y-axis. When our values of y greater than that, it would be up above again. So now I have to shade above. And notice when we shade above, I'm going to go all the way kind of over here on that right-hand side. If we have overlap, then there's a solution to the system, and it looks like we do. So what I want you to do is either just shade in that overlap, or make sure to darken it in carefully to show that every ordered pair in that system, or in that set of shaded region, would be a true, wow, I can't think of words to say today. Sorry, you guys. Every ordered pair in that shaded region, that darkened in region, would make both inequalities true at the same time. In our next example, the issue we need to tackle first is isolating the y variable. You want to make sure that y is on the left side of the inequality so that it'll be in agreement with your shading. If we take a look at that first inequality, x plus y is greater than 2, what I'm going to do is take that and isolate y, meaning I'm just going to subtract 2 to the other side. And that gives us y is greater than negative x plus 2. Go ahead and graph that line with a slope of 2, a y-intercept of 2, and a slope of negative 1. I'm going to put my points all the way through the graph on the bottom over here, and then of course up here on the top, so we can get that nice linear appearance happening on this graph. Notice because of the type of inequality, it's going to be a dotted or dashed line. We could almost leave it like that, but I'm going to put dashes through it just to give myself a little bit more of a location on here. There we go, with arrows on the bottom and the top. Greater than, again, means to shade above. Not quite sure why they're all like this, but that's just the case today. If I look at the y-axis where 2 is located, when y is greater than, it would once again be to the top. So that means I'll shade everything on this top part, like so. If we take a look at the next inequality, 2x minus y is greater than 1. Let's isolate x first. Y. So we'll subtract 2x. And then we have negative y is greater than negative 2x plus 1. All of a sudden we divide by negative 1. And when you divide an inequality by a negative number, it actually switches your sign. So see what happened there. Negative 2 divided by negative 1 would be positive 2x. 1 divided by negative 1 would be negative 1. That's going to change how we graph this inequality. Now I'm going to start at negative 1. On the y-axis, a slope of 2, I'll count up and over. We'll go all the way up like so. The other direction, down 2, 1 to the left, like so. Now this inequality is just less than. It also will be a dotted or dashed boundary line. Go ahead and draw that in. There we go. And now when values are less than, if I go to where it crosses the y-axis at negative 1, y values would be less than down below the line. So that's where we will shade. As I go through this, I do see a significant amount of overlap, kind of all the way over here on that right-hand side. That would be the solution to the system of linear inequalities. There are technically infinitely many ordered pair solutions that if we substituted their x and y values in to each inequality, it would be a true inequality statement. There's the solution to your system. This next system has us looking at more than 2 at once. But again, our plan is to just sketch one inequality at a time, find its shaded solution, and as we go through this process, we should be able to get a solution to the entire system. But I'm not going to start with the first one. I'm actually going to start with the third one. X is greater than or equal to 0. If you have just x, the plan is going to be a vertical line, almost like an axis of symmetry. So if it's at 0, that means it's crossing right here. We want a vertical line. Oops, that's going to be solid because of the greater than or equal. I knew that. There we go. Draw that in. Hopefully you can see that on your paper, all the way from top to bottom. And it says greater than. So if we look at the x-axis at 0, when our x value is greater than 0, that would be to the right. So I'm just going to kind of lightly shade this whole right-hand side in. That would be that x is greater than or equal to 0 inequality. I'm going to do the y inequality next. And that does the same thing, you guys. If it's y equals 0 for our boundary, that's horizontal. Go to where y equals 0. This will also be solid, and we'll have a solid horizontal line from left to right all the way through. And it's greater than or equal to 0. So when are the y values greater than? That would be up above. Now as we look at this, they really only match in quadrant 1 so far. It'll depend on what the blue and the red look like to get our final answer when we're done. Taking a look at that first inequality, 2x plus y is less than or equal to 14. We need to isolate the y variable. This shouldn't be too difficult to do if we subtract 2x. But we run into a little bit of an issue, negative 2x plus 14. The y-intercept is significantly off of our graph. So I'm going to look at other options. Let's see what we could do here. If the y-intercept would be 0, 14, and that's too high up there, maybe I'll move over to, I don't know, I'll try 4. If I plug in 4 for x, negative 2 times 4 is negative 8. And negative 8 plus 14 would be 6. If I graph 4 and then up 6, I know that that point is on my boundary line. To get the rest of them, I could now use my slope. Count down 2 over 1. Ooh, and this is going to get kind of messy. Down 2 over 1 and keep going all the way to the edge of my graph. And then I'll go in the other direction, up 2, 1 to the left, up 2, 1 to the left. Those appear to be collinear, meaning on the same line. So now this is going to be a solid diagonal boundary line. I'll draw that in. Go all the way through your graph, like so. And it says y is less than. So way up here at the top at 14, values will be less than down below. So now we've got to shade everything in this way. Oofda, this is getting to be crazy. Can you tell what our shape is so far? It looks like it's a triangle. The blue, the green, and the purple overlap to form a triangle. But we have one more. All right, let's see here. And that one is x plus 2y is less than or equal to 10. If we subtract x, we get 2y is less than or equal to negative x plus 10. Isolate y, dividing both sides by 2, and that gives us y is less than or equal to negative 1/2 x plus 5. Well, that looks like it should be easy enough to graph. The y-intercept is 5. Let me see if I can find that in this mess right here. So I'm going to count down 1 and 2 to the right, down 1, 2 to the right, and so on. And then up 1, 2 to the left, all the way to the edge of my graph. Looking at that inequality, that should be a solid line. Oh, goodness. All right, let's see. Here we go. Draw that in. And we want to shade below because it's a less than or equal to. So on that red line, when are values below the y-intercept? Down here. So now let's see what we've got. Oh, alrighty. Way up there and so on, all down here. Can you tell where our solution is? I see that my green line is here. The purple line is here. The blue is right here. And then that red. So we're kind of forming a little bit of a quadrilateral. And if we darken in this solution set, boy, this got messy. It was fun to color though. What that tells us is any ordered pair in that shaded region would make all 4 of those linear inequality statements true. Tomorrow, we'll do the application problem.